When my face gets squared, I don't really feel it that much. It's so
You reckon it's slapping his head with the belt?
No. I'm not gonna smack him. That's why I sat here, because I didn't want to be in the fan. No, you can leave it. He's very much enjoying it.
I was enjoying it.
You want it all the way back up?
I just didn't want to stand, like, sit here and have it, like...
No, it was putting on my face directly, so that's why.
Javed, you were 100% right, what we talked about. It's pretty red.
One is sucked down, another
I think
one
that serves the same purpose.
It will take me maybe 2 minutes more to
Oh, never mind. There's this little
download stuff, but
camera.
Selfie camera.
Yeah, that's the front-facing one. With the bubble in here. It's like,
There's a delay for the front-facing.
I guess. I mean, apparently there is.
People are so slow that when they hit the button, they're not ready. Oof,
It's like I hit it.
Apparently he
Then it
is.
takes a picture.
Oh wait, what the fuck? No, I took it right. Oh, I don't know, that's weird. It's gonna use the other camera.
Roy and Jabet will especially enjoy the first talk. And the presenter of the first talk will very much enjoy their comments. David
Not me.
Graupner,
Apparently it's me.
he will be speaking first, and he will share his vision on the autocorrelation function.
Oh, no.
I don't want to start this fight again.
There are two possible outcomes. Either he will resolve your thermal conflict, or maybe you both will kill him on this subject.
No, haven't we came to an internal
I find option
agreement?
2 far more
We
likely.
have yet to
I guess
convince our
my
advisor.
concern was interpreted wrong differently.
Hi, Fatima, how are you?
Yeah, but now we just have to convince our advisor still. So we are in agreement with not her agreement.
Yeah.
Well then maybe you should give the first presentation.
No.
Wait, no. They're not allowed to speak on it because they will speak for 4 hours without conclusions. They do it in their free time. They're clashing in the interpretation of this function.
No, now we're done. T is just delay time.
Yeah.
You don't get out of it that easily.
Yeah. Like a tablet.
So we were scheduling a little talk on how to install MATLAB, but it seems trivial, so we can skip it. If
This is next.
maybe once in the future. So let's.
Something like that.
If you're using that, you probably have to drag something.
Yeah. Just download the image and then you copy it to your application.
You just download it and select how many modules you want to install. And then it will take long time to download the line. It was very big.
Oh, good. It's only 6 slides.
Well, there are 5 talks. 6 slides only on this subject.
5 talks. Wow.
Mine's got 6 slides.
So
This group meeting is so much different than this office.
The idea is that we need to get some practical skills overview before we go to actual scientific results.
How about the first one? Oh boy.
So, if you want to present next time, you can sign up what is your favorite subject. I will put a little piece of paper for your final decision, and these two pieces are just for your information. If you really want to.
Kamsahamnida.
It means happy birthday in Korean. No, just thank you.
Thank you very
Complicated.
much.
Complicated. And one more piece of paper, just with your name near the subject you really want to present. So the first speaker is David. Since your slides are the shortest ones, do not hesitate to go over time and hear of what our audience will ask you. And let me quickly introduce what we are doing. So the goal of most of us in research aspect is to investigate, model, follow, monitor photo-induced dynamics of electrons and holes and excitons. And there are several approaches, some of which are based on autho-correlation function, Redfield tensor, and propagating of density metrics in time. We are not, these meetings are not theory meetings with deriving equations. It's more practical skills how to operate already existing software so we can go quickly to applications. And today's meeting is chopped on several steps that one need to cover towards describing realistic models, and David, so there will be converting couplings into Redfield tensor, running electron dynamics, and then there will be several aspects of how the specifics of this procedure changes if you treat explicitly momentum or you have nonadiabatic coupling and such. But without talk of David, no of other steps are possible. So, special speaker for special subject.
So, as Dimitri said, what I'm talking about is auto-correlation functions and running them. So the auto-correlation, and the equation I have on here is just regular correlation, but if you would change the G to an F, it would be auto-correlation. Describes how similar the functions are as a change in time. And to get this, we need some codes, and so we need our MATLAB code, which is a correlation _V and then some number. You're also going to need your coupling files that I think Yulun explained how to get a couple weeks ago. And you're going to need the energy pop file, which you obtained from your geometry optimization runs. It's the same file that you would get your absorption spectra with. And you're going to get some output files, which are kind of covered up here. You're going to have some correlation files and RRR file. And wasn't entirely sure how to integrate this into my talk, but I was asked to talk about the Bandel file, which is an integration of the par charge files. So it takes the par charge files and integrates them down to either 2 or 1 dimension. And the code for that is in the bin. The only place I could find where the code was in one of Yulun's old presentations. but I wasn't able to actually test it before I tried this or put this together.
Yeah, we need to agree on having public available repository so that we can standardize names and every of us can put updated versions there and
Yeah, the only place I could find it was I was going through your YouTube links and it was on one of Yulin's old talks. It's the only place I could find
explanation.
the explanation.
The actual code you have, right?
The
MATLAB code to run stuff.
Make the correlations and the like.
Yes.
Yeah.
Okay.
Yeah, I have this file. This is about the Bando file.
Oh, okay.
So
there were no questions about definitions?
When you say it describes how similar a quantity is in space or time, like what quantity would we use it for?
So it's describing the function. If
Like
you,
a function of, like what function?
Let it be used.
So what would be the correlation of sine?
how much they overlap?
What's the number?
90 degrees. 0. Oh, I see.
Right? But if
Yeah.
you sine of sine,
Then they overlap.
then it's, if you normalize it's 1, right?
Yeah.
So it really tells you the degree of like frequencies that coincide. And I think you use this so that you can see if your system has memory, because the autocorrelation function is used to see if there's like periodicity in your function, and if the nonadiabatic coupling terms are long, like if there's a lot of like hysteresis or memory, then green field, I think, whatever field you use.
Are you using hysteresis and memory kind of
Yeah.
synonymously?
Yeah, sorry, I should have not said that.
So
like memory.
I was going to ask you
Yeah.
hysteresis. So.
Yeah, so like if you do an autocorrelation function, then you will see which frequencies are like within the function that are clean. So like you might have noise, but the autocorrelation function tends to clean up that noise. Okay. Is that correct?
Nothing strange. Everyone is happy? So, since you have seen next slides of your talk,
Yep.
autocorrelation of which function you are going to find?
So autocorrelation of the energy of the orbitals.
It is Jabet and Levi clashing into each other about this one. You are going to find autocorrelation of some other function. In your green space input files.
Yep.
So what is XXX?
The coupling between the different positions. So
Coupling between different. Up to here it was correct.
coupling between different time steps in our molecular dynamics run.
Technically correct, but it's couplings maybe between orbitals or couplings between electronic and nuclear degrees of freedom. And what are XXX?
The number representing which specific time steps you're looking at.
Okay, so you have many of those files.
Yes.
So this non-adiabatic couplings along trajectory, along timeline. And you are going to find out the correlation of these non-adiabatic couplings.
Yeah.
Perfect. Do not hesitate to tell it again and again, with or without reason. So, what is how do the coupling files look like?
They're a string of matrices.
Okay, but if in this matrix you pick up one number, like element line 1, column 2, and compare it in each of these files along your trajectory. I know that most of us do not do this experiment, but imagine you do it. What you would see?
A decrease,
Mm-mm.
a increase,
Mm-mm.
a zero.
No, both. There is like. So if you would look on them, they will rapidly change. So for a given pair of orbitals, the amplitude of this coupling would be near some average value. But it will fluctuate or oscillate very quickly from time to time because of phase effects. And there is no a single point along the trajectory where the individual coupling file will be represented. So it will be very random. If you take like coupling between Homo and Lumo and look at each point of time, it will drastically positive, negative, and we have avoided it in current version, but generally it is a complex. So it is oscillating in the complex plane,
Okay.
which is not comfortable for humans. So one needs an average procedure that extracts most reliable value of this intensity. So you are finding autocorrelation of non-adiabatic couplings, and the reason is because it is very noisy data. Yeah, thank you.
So this is the MATLAB code, and it continues on farther. And this is a fairly robust code. One of the major things we need to watch when we run this is we need to make sure to change this for our specific system. You have your Homo, and then you have the lowest orbital you're looking at and the highest orbital you're looking at, much like the input overlap file.
So is there a reason why you have like twice as many unoccupied orbitals as you have occupied orbitals?
I have no idea. I
Okay.
just took this file as it was saved. Do you know if there was a reason?
Well, this is not a subject of history, right?
I suppose it could have just been like the same energy interval on either side, which just wound up being different numbers of orbitals.
But as soon as the specific researcher started computation of couplings, the code that computes autocorrelation cannot change and select different range. It's just matching input and output between different modules. So it's question why the couplings were computed for this strange range, but not to the code or not to the speaker in his current function.
So here we can see the correlation function. You can see a rapid decrease, and then it fluctuates throughout. And if it gets small fluctuations as time goes through it, go by.
There will be questions.
That graph of the autocorrelation function?
Yes.
So someone in the audience will definitely ask 3 questions. What is x-axis? What is y-axis? And since there are so many pairs of orbitals in this coupling matrices, for which pair of orbitals one draws this autocorrelation? And it's fine to make the just best guess.
So x is a time step.
But it is not absolute time.
No.
It is offset. In your equation, it is like tau.
Yeah, it's a time step.
It's offset between your functions, right? 0 means it is the functions are selected to coincide.
And y is the overlap of the two time steps or orbitals, or
Basically, autocorrelation.
yeah. I do not know what orbitals we're looking at.
But maybe it's something frontier, like either
I would assume
like Luma to Luma plus 1 or
something close to the band gap, but I am not sure.
So is this a normalized autocorrelation function, or is it not normalized?
No. Now you may want to ask Levi and Janet before going forward, like what they would expect from this figure before you show it, and how happy they are for the autocorrelation to drop down so quickly. And just listen what they will. You ask yourself and look at them.
So to me, this says that your nonadiabatic coupling terms are non-correlated. So there's no like memory in the system because it's not really periodic. So if you took the FFT of this, you wouldn't really get any frequencies that are dominant because it's pretty much just white noise. The other thing that I kind of am learning to be pickier on is the time, your protein. So you probably didn't run these calculations, but the more I do autocorrelation function, the more I know that the protein has to be smaller than it needs to be for classical / quantum approximation for dynamics.
So if you would redo this calculation yourself, you would select protein like 100 times smaller.
No, like it looks like
10 times smaller to focus on the. To have
it
more
looks
con-
like the protein was 2. 1? Okay. So maybe half of a femtosecond. But when I was doing mine, Patrick ran 5 femtosecond, and then if you try and do dephasing off of the autocorrelation function, you get nothing.
And so in your experience, how quick autocorrelation function for your orbital energies, how quick it decreases? Here it decreases instantaneously. within-
Yeah, ours doesn't do it as like if you do energy on orbitals, then it's much longer. Than,
How many? Here it's about 1 femtosecond, and in your case, how long will it take to drop down?
I don't remember off the top of my head, but
Like
It-
10, 100, 1,000.
it's probably like 100. So like drops off pretty quick, and then
like
it
5 or 10.
like oscillates still. So it's kind of like an exponential function and a sine, where like your fit for tau for the exponential is like 1, where ours is like 50 or something. But it's since I've talked to you about autocorrelation function for nonadiabatic couplings, it doesn't surprise me.
This is much shorter.
Yeah.
No more questions? Then let's go forward.
So here we see the same graph, except in this one, the x-axis is a logarithmic scale. And what this allows you to do is see the early time steps much better.
So that's the same thing, just zoomed in.
It's the same thing, except the x-axis is logarithmic now.
So one is 10 femtoseconds?
Yeah.
Everyone seems happy.
So one of the other outputs from the file is the Redfield tensor.
Maybe not one of the main.
Okay, the main. And I have two representations of that here. And once again, the difference between it is this side uses a logarithmic scale in the z-axis. This side does not. And if we look at it, the x and the y are orbitals with the HOMO and LUMO being in the middle. 10 and 11 looking at it.
Is there a scientific reason why you do log of r plus 17? Or 17 just so that you can visualize it?
Last one.
Just
I was going to ask that because I tried that once, but it just gave like, it didn't give bars. It gave like just planes.
So yeah, it gives you all these extra peaks off to the side here that you don't have on just the straight number.
Right. So is 17 special? Because
Not that I know of.
Probably.
Yeah, it is magic number.
no, but looking at the non-log, it goes only to 0.1.
And 17 should be out of brackets. No?
Oh, you add 7?
17 should be out of brackets. Like logarithm r plus 17.
No, because
Then
it only
17
goes up to
means
5.
10.
It's less than 5 if you go like 0, 20.
What's the point of shifting it by 7?
Oh wait, no, yeah, you're right.
Would you like to explain? Do your best first.
For Ri is a very small number to visualize it just to say 17.
Mm-hmm.
It's a very small coupling, so it's not visible in the picture. So not
David, you don't have chance to raise the voice. David, you're right. So the left figure shows that for human eye, everything except main subdiagonals looks like 0. And if you take log, it will be like 10 to minus 17.
What's the importance of that tiny coupling compared to the diagonal?
It is extremely important, and it is the only way why I want to believe that we are more competitive than Nathan and his boss. So,
Ugly Andre is not here.
so there are alternative ways to do the same. How Professor Nsibi repeats in public, there are several ways to skin a cat. I do not make this analogy. So there are several ways to compute nonadiabatic couplings and dynamics of excited state. And in the group of Zakrzewski, one practices non-adiabatic couplings as a response of electronic structure to the shift of system along normal modes. So one assumes that upon thermalization, there is only excitations in the harmonic nuclear vibrations. while at our side we do not care. This molecular dynamics may have unharmonicity. And if one processes couplings under harmonic approximation, then several transitions are completely disabled. Not to numerical precision, but they are absolute zero, 10 to minus 3 times. And as soon as unharmonicity is brought in, some transitions become non-favorable but still possible. 10 to minus 70 when Jevon is asking the meaning of this small but non-zero values. And if we practice couplings based on trajectory, then air photo excitation will always relax to homo lumen, and then if our code allows, it will combine from homo to lumen. While in the normal mode approaches, there are some sub-gaps, for example, between lumen plus 1 and lumen, that do not match in resonance are not in resonance with any of normal modes, and transitions will be absolutely disabled. So the system will get stuck on, let's say, lumen plus 1 or lumen plus 10, and will never go forward. And this is unfeasible. So as soon as normal modes approach doesn't run into this little difficulty, then normal mode is really good because it is, goes along with all definitions and things. But this approach allows to overcome it and even not to think about it. Very good question. Okay. Sorry for interrupting. Okay. Any more questions to the speaker?
If you take a autho-correlation function of very correlated system, what kind of graph you are expecting compared to whatever you got now in slide 4?
One that should be close to 1 throughout.
Yes. So it
And
will
theoretically it should
it will drop to zero, not as quick, but very slowly. So it will drop and approach to zero at much longer time scale.
Now, I would say that it oscillates between 1 and -1.
If you consider mathematical example,
Yeah.
and but if you look on any practical
But-
examples with a little bit of noise, it will always
But
increase.
the time that it drops does not relate to the correlation. It relates to the frequency at which the function goes up and down. So it could still oscillate crazily, but it's
But it will be periodical in this.
Yes, it will be more
It have a
periodic.
constant phase
it
difference.
won't drop slowly if the frequency is fast.
So sine and cosine would be correlated because as you shift, they'll come in and out of phase
Yeah.
with each other.
Yes. But it really depends on the frequency, because that will dictate how fast it moves up and down. And then, like if you look at the envelope function, that would tell you what's going on.
Now you see how they can keep discussing for hours and days and weeks.
Okay.
Kevin, you will need to do the same calculation in like hours or days. So if you have any questions, ask me now. Does it seem reasonable, the procedure, or you need to practice before you ask?
I need to practice before I ask.
Okay. Okay, let's thank David once again. Next presentation is by Dr. Han. So it will be a little more slides. Maybe it will be less discussion. You'll find it. It's good. like number 3. So this so in the previous talk, we had difference between approach of Dr. Peresky and other 2 theoretical groups. So we were still allies with Levi and Jerry. And now we are forking more and more away. So although we do couplings in the same way, right now the procedure for running electron dynamics will be very different. So instead of surface hopping that a lot of people are using, here it will be density matrix propagation. Which, Dr. Han will show details how to utilize triple R files that David, so to say, has generated for everyone in order to see what excited electrons and holes are doing from practical aspect.
Okay, so to do the non-adiabatic coupling calculations, we need some input fields. So first we need the triple R file, we need the energy part, format-3Q, channel, and this special MATLAB code. So this is the format-3Q. It's also is stressed in matrix format. And we use this command line to generate the format-3Q. And this is how it looks like.
So it's values of oscillator strengths for each pair of orbital.
Right. And this is how we get the band file. So we need a special income, and also we need, after we run that, we need to run this band. So I guess to use this command, we need to modify 2 parameters. We need to change the orbital number here. So after that, we run this per command, and we can get the band file.
So is it the universal command, or there are some modifications of this band integrator? Will it work for VASP5, or there are some?
I guess for this is just for VASP4, but in the bin there is another code. I guess it's band integrate 5.
Okay.
And here we need to make sure all these input files are in the same folder, so we can run the MATLAB code. So, any questions so far?
Especially clear. So feel free to stop.
Right.
David and Kevin are main audience of these talks. Do not hesitate to stop if you want more details and clarification.
Do you want to have a question? Okay, so next we take a look at the MATLAB code. So basically in this code we want to get 3 main outcomes. The first one is evolution of orbital occupation as a function of time. The second is charge distribution as a function of energy. The third is charge distribution as a function of space. And in our calculations, we separate electrons and holes. So there is an approximation, there is no interaction between electron and holes. So this is the start of our code. So IH stands for initial condition for hole, IE is the initial condition for electron. So IE equal 10 means this is 9 octaves above Luma. This is 9 octaves below Luma. So since there is no interaction between electron and probe, I will only focus on electrons. I guess this is another recording. This is just because any path has 3 columns, and we transfer different columns to different files. So here for this line, we just load the triple R file and we mail it for ME. And here we need to modify some input. We need to specify a global level and the start of the orbital and the end of the orbital. So this is the visualization for RR. And we can see there are 2 parts. The blue stands for hole, and the yellow stands for electrons. So since there is no interaction, we can just separate them. So this is what does this command do. So basically, we just choose certain part of the RR file. And for this block of lines, I guess for RR, we have transition rates for forward transitions and backward transitions, and they have the same value. For example, the transition rate from LUMO plus 1 to LUMO is equal to the transition rate from LUMO to LUMO plus 1. So since they are equal, we can just cancel out one set of data. We only focus on transitions which lead to minimization of total energy. In other words, we only keep downward transitions from LUMO, for example, from LUMO plus 1 to LUMO.
Let's ask Jabba, Levi, and Nathan how they would call this procedure and how they treat it in their approach, so that we have more discussion and more ability.
So is this?
There is a name in statistical theory. Principle of. First, there are 2 words for. First starts with letter D. Second starts with letter B. No. Second word starts with letter B. If you took statistical mechanics, you should recognize it. Huh?
But in our approach, we just make it 0.
I apologize for this little break, but it is justified.
What is the question?
Yeah, what is the principal state again?
Let's play this game if you will, maybe.
Coupling I to
Otherwise, no one of us is. Huh? What?
No, I'm just telling him words.
Alright, say that one more
So
time.
it's a 2 step.
Yeah.
So coupling between this state and that state is the same as that state to this.
Oh, okay.
So electron, the relaxing and exciting both are the same.
Yeah.
Detailed
And in
balance.
this case,
Yes, Levi is correct.
Because I wasn't really paying attention that much. Yes. But we do
Detailed
it,
balance.
we do it by using a Boltzmann factor.
Right? So first D, second B.
Detailed what?
Detailed balance.
Detailed balance?
So yes, transitions down in energy are enhanced, transitions up in energy are suppressed. Right? And you are doing it through Boltzmann distributions in surface coupling.
Yeah, so if the energy is down, then the exponential is large. If it's up, the exponential is virtually zero.
And in the limit of lower temperatures, transitions up become more and more suppressed, and the approximation that Yulun has presented becomes more and more valid. If the temperature goes to infinity, then transitions up and down become equivalent.
And the electronic structure goes to...
Yes. Firm distribution has very continuous, no step. Everything is occupied. Okay. How do you do it in your approach? Put you on the spot with a camera.
I think I have an answer.
So the transitions are multiplied by both, in your approach they are multiplied by Gauss-Einstein distribution. So based on thermal occupations in each of the following modes, the resonance transitions up and down are multiplied by a certain factor. And there is the same physics of transitions down in energy are hence transitions up in energy are suppressed. So what is shown on the board is an approximation that just saves some numerical efforts, but it works quick and efficient.
Because here, what matters is setup of time. So we first create a T grid, and it is from 1 to time step. So usually we use 600 as a time step. So T grid as matrix, it goes from 1, 2, 3 until 600. And for each value of T grid, there is a time associated with it. And this time, we use this expression. So basically, it's just like the size of this time increase exponentially. So for example, at the initial value of the T grid, the time is like from the second, but at the end of the T grid, it's like kilosecond.
Let's discuss for a bit. So what would happen to propagation of differential equations with Runge-Kutta method as you do in surface coping if you escalate time step in this way? So when you do step 3 in your surface coping, your time step is smaller than femtosecond. It's like attosecond or 10 attoseconds. And the time step is used because electronic occupations are propagated by solving differential equations forward in time. Right? While numerically solving ordinary differential equations, precision of answer does depend on the step size. If you decrease step size, precision increases. If you increase step size, precision decreases. What if you exponentially increase step size as you go forward and forward? What happen to your precision? Huh? Yeah, it will blow up. Results will become unreliable very quick. Huh?
We have other rectangle rules for integration of differentials in discrete function.
Because you are integrating differential equations. Because you are integrating at each time step. But you should get intrigued by this approximation. Because it will not work for numerical solution of differential equations, right?
No,
So on intuitive glance, this escalated time step will ruin any numerical solution. On other way, if one can do it, it will mount wings behind your shoulders and allow to describe times to nanoseconds or microseconds, right? How can you simulate with surface coding? What is the longest trajectory you can do in a reasonable time?
I use around like about 4.4 picosecond.
Okay, so
So that's my
5
longest
picoseconds.
5 picosecond.
Now watch what you have. Yeah.
So
Oh.
I guess I have a question too. Is this the time step on the figure that's on the next slide? Is that why like there's no actual meaning behind that time step? Okay, that makes so much more sense now.
So I guess one of the most important output is this figure. So the next few slides explain how we calculate this figure. So I guess we start with PDE. So this is a matrix. It's orbital times time steps. So the initial value of PDE is set up in such a way that at the initial time, the initial condition is 1, and all other elements are 0. So and then next we diagonalize it the electron part of the triple armor file. So there is a correspondence with this equation. So this is Lewis Wheel and Redfield operator acting on eigenvectors of density matrix. So you can get the eigenfrequency and the eigenvectors.
Let's wait if there are questions. So Levi and Jabet are not going into active discussion. You may object for initial condition of only one orbital excited. Okay, if you don't care, I'm fine. And another here is the resolution of the intrigue, like that was posed by previous slide. How can we escalate the time step? So if our ordinary differential equation has constant coefficients, instead of propagating by infinitesimal time step, again and again, one can diagonalize once and have solution. It's like between analytical and numerical. It is numerical, but it is not time propagation. Just by finding eigenvalues and then expanding solution as a superposition of eigenvectors with time factors depending on eigenvalues.
Don't you do several different orbital initial conditions? You just,
One can do it, but
you just look
the
at
life is busy even without it.
Just take the most optimal.
like it's not that you don't need. It's not that you are forced to. It's that you don't need to, and you have reasons to look at specific transitions.
And other questions about the last line? Is everyone happy about this semantics?
The one that's circled in red.
Huh? Yes.
Can you explain what the EIG command is?
This is a function of MATLAB. So what they do is just by typing this command, we got two kinds of data. The first one is the eigenvector, which is U. The other one is the eigenvalue, which is D.
So finding eigenvectors and eigenvectors, and they are directed into two matrices. So the first U will be a set of eigenvectors composed into a matrix, and second, D is eigenvalues where diagonal elements will have eigenvalues and all the rest will be zeros.
All right.
The reason this code is in MATLAB rather than in Fortran, although there is a goal to rewrite it in Fortran and it will be so much quicker to do this, that commands like this take substantially larger number of lines and are harder to debug.
Next, we calculate some expansion coefficient. So this is our initial condition. This is the eigenvector. So the meaning of this is a degree of contribution of each eigenvector to the initial condition.
Everyone is happy? So this one is solving algebraic matrix equation. Like if matrix A times unknown vector x equals vector c, then x will be equal matrix A backslash the matrix C. So it's decomposition of the initial condition, which can be anything we request as users, on to eigenvectors, which will be specific, which are specific and depend on this matrix derived from nonadiabatic couplings. Oh, Kevin, please.
Okay, so I just want to make sure I understand what we do. So the whole purpose of this talk is to like learn how to create all the MATLAB input files from the data we got in VASP.
You can say so, and in a little from different angle, which steps I needed to make MATLAB code to generate figures like the one shown in the upper right.
Okay, so then in VASP we extract the files for master EQ and then band out, and then we use MATLAB to extract data from those input files and then put them into variables.
And then apply specific methodology to predict how electrons and holes will change in time, which orbitals they will occupy if we perturb system by light.
Okay.
Make sense?
Mm-hmm.
So yes, now we can populate the PPE file. So from previous slides, we can get the eigenvector, we can get eigenfrequency, and we already set up the time. So this is just the coefficient C. So this is the projection of the initial condition onto eigenvectors. So we can use this equation. This index just tells us to run over all eigenvectors. So we can use this equation to populate the PPE file. So here are some details.
Let's give a second.
What is IB? What is the equation?
Huh?
What is the superscript IB?
Initial conditions. It doesn't need to be. Can I answer this? So it deals with the question raised by Levi. Are we mandated to have single orbital occupation as initial condition? No, we are not. It's just one can answer a lot of, get a lot of insights about system by this simple arrangement. And this code without any changes can be used. Like one can use excitonic initial conditions or superposition of conditions when several alpha parts are in superposition. But traditionally, just as a simplest thing, we use single orbital excitation. And this notation here tries to make things specific. So rho with superscript AB means it is initial condition of density matrix which has been created by promoting electron from occupied orbital A to unoccupied orbital B. And IJ runs for almost.
So with this, we can finally get this kind of figure. So as we can see, the initial condition is the orbital occupation is 1 at initial time, and as time goes by, the initial condition improves occupation, but other states just get some fractional occupation. And finally, for example, at 600 time step, the final state, the null has occupation 1. All other orbitals have occupation 0. This I just stand for some numerical evaluation. This is why some very important.
Yeah, things work without these 3 lines. They're just in case of numerical errors accumulate and lead us away from normalized occupations. This will bring back to restore normalization.
So finally, the data stored in PDE is at each time step the fractional occupation of each orbital. So here is a distribution of charge as a function of time and energy. So this is our PDE, and this is a distribution function centered at the orbital energy. So for this equation, we just minus a quick value.
Either no questions or no one cares.
Here are just some parameters we use to generate this figure. But I guess we should pay attention to this one right here. So this is the expectation values. This corresponds to the solid and gas field. So there is the equation we use to generate the expectation values. It's of the occupation of the energy at each time step, at a specific time step. And finally, we just sum it up. Here is just some, use single exponential thinking to get the weight. This is a final output. This is a weight for electrons.
Okay, thank you. So, are there more questions? Especially, oh, please.
So, how can you assume that it's a single exponential fitting for the occupied orbitals. Because you have an obvious intermediate state. So
it's like a double expansion line.
yeah,
So I guess area has a river. We compare the single expansion and some double expansion. I guess the difference is 30%.
Well, basically, you just do more work. That's just what the code spits out at you. But
Yes.
you obviously see it's not single exponential
but
decay.
it's not even bi-exponential.
Right, you would have to do some sort of.
Is it
curve there.
stepwise single exponential? Seems like that.
No, you have to do a kinetic model.
But it's
Okay.
stepwise. It's like, is all population is relaxed to the intermediate one and then is relaxing directly to the lowest.
I guess I beg to differ that it can be fit to a double exponential.
It's like A to B, finished everything, and then B to C. So it's like a step which is going there.
Yes.
I'm not sure. I'm just assuming
Okay.
that my answer.
I'm just going to not argue.
One thing you do is just break it into two trajectories so that it decays to the first level, assuming it fully populates that one.
Yeah, so
but
we
that
have full
is
level.
a highly
Then another
crude
one.
approximation, and it's very easy to do a kinetic model that would be nearly the same amount of work.
That's
Well,
also kinetic model.
in some sense, this code is like 200 state kinetic model.
Say what?
Kinetic model.
No, this is also kinetic
not
model.
to
Their
find
kinetic is going stepwise.
Not
Okay.
here, but
Oh.
original data with occupations.
Yes.
So, the data that you are proposing to use through kinetic model are already there. One can return back to occupations of space versus time, and everything will be there.
The biggie, that data set. So like the
Yeah,
average.
but you can also just look at the transformation from the nonadiabatic coupling terms to your Redfield tensor, because isn't that in rates? Your big matrix that has, isn't that rates already? So you could just look at that without doing anything.
Exactly,
And say,
exactly.
this is what it's going to
But for you as a human, do you like to look on 100 by 100 metrics and analyze it?
No.
It's better to have one number, maybe not very precise, but which gives you insight into behavior of a system. With understanding that additional data are available, but no one needs it. More questions? Okay, if no, let's thank you once again. Please feel free and go ahead and asking each other, especially Kevin and David, because you'll get questions while trying to do this. And the next special speaker for the special subject is Landon. So let's check how much his talk is different from.
It's going to be a little different. Mine is pretty much
So
how
it's
do you do the thing.
similar things, but from different angle of view, right?
Yes. Alright, so mostly what I'm talking about is just kind of getting your data, manipulating it a little bit, just initial conditions with this same script that we've been looking at. Okay, so if you look over here, this is, in the first 20 lines of the code. Just make sure that you have all this stuff set appropriately, and you guys have already talked about that, so I think that you already know how to fill that out. The big thing that you're going to be changing when you, run and rerun this code over and over again is the initial conditions. So, like Yulun had said earlier, this is the initial state of the hole and the initial state for the electron. So what you're saying right here is, I'm photo-exciting this electron into this orbital, right, and it came from this one. That's what these IH and IEs are. And then you're letting the code figure out how they relax back down to the frontier orbitals. And so, yeah, you'll see that this is obviously not in the index of the orbitals, so the way that you sort of think about what these numbers are basically is this number basically tells you how far into whichever band you actually are. So IH equals 1 is the HOMO, IE equals 1 is the LUMO. And so if you go to, like, say, HOMO minus 1, that would be IH equals 2, HOMO minus 2 would be IH equals 3, and so on and so on. And then vice versa for the IE and the electrons. So the way that, at least that I figure out how to, I guess, like, what numbers to use for these is you look at the OS strength file. Let's see, because the OS strength file is rated in descending order of oscillator strengths. So what that means is that these top handful of rows here are going to be the most probable photo excitations to happen if you were to just shine whatever incoherent light on it. And these are the energy differences too right here, by the way. So, like, if you're looking specifically for, you know, like 3.5 eV photons, and, you know, you just want to stick with excitations, I guess, that kind of match that criteria. So what you're going to do is you're going to take these and convert them into the IH and the IE. So I guess in order to do that, you need to know what your HOMO is, but that should be right there looking at you anyway. So you see that 450 is 4 orbitals into the valence band, right? Because you got 453, 452, 451, 450. So that means that IH would be 4 in this case. And likewise, this is 13 states above the LUMO, so it's going to be 13 plus 1, right? So you get 14 for your IE. So once you do that and you try to run your code, and hopefully it doesn't crash on you and you actually get results. Yulun had already kind of talked about these. These are a very big one. But you'll also get these green figures, and I guess, do you guys know, like, how to interpret these? I mean, have you seen enough of them, I guess, or is it still kind of iffy? That's mostly what this slide is. And then I pasted the system that this was for right there, so you can kind of see. Okay, yeah.
I'm just selling copies of your masterpiece.
So what these figures are telling you is so you have, like, some instant in time, right? So you got, like, some vertical strip here. So in this case, this is the position versus time. So what that's telling you is that each position, right, in your system, which corresponds to the vertical spot right here, the other 2 dimensions are just integrated out. If you're seeing just this background green color, that means that the charge density is the same as it was in the ground state, so it might as well be the ground state at that position. So, like, say, you know, initially right here in the titanium dioxide, there's really no change right after you've done your photo excitation. It's...
Yeah. Is it okay?
Yeah.
So, our audience is split on 2 parts.
Yeah.
In a sense. So one part is looking for optical signatures, like photoluminescence, and another part looking onto charge transfer, charge current density. So which of these parts your slide is primarily directed to?
This would be for absorption, not luminescence.
Charge transfer.
Yes, charge transfer.
So it's more for electronic rather than optical applications.
Correct.
So,
Yes.
On your opinion, who would appreciate the slide more, David or Kevin?
I can't remember what you guys are doing right now, so I don't know.
Ask them. It's very informal.
What are you guys looking into at the moment?
I'm studying PPTE nanowires.
Okay. Like, what about them, I guess? Like, are you looking at optical properties, or?
Which application?
Okay, so I guess for my nanowires,
Yeah.
I'm specifically looking to see how durable they will be at, like, higher temperatures, so like semiconductors.
Okay.
But what is application of these materials? Which
Is it a lead in a diode, or is it like solar cell?
Either one. The third one. You know it. Don't worry. So both you and Kurt, who was presenting after you in class, introduced why those materials are needed. I have a written record of you answering this question in the past. First letter C, T, T. Second is two words. And second part of the word is E.
Thermoelectric.
Yes. Is there charge transfer involved in thermoelectrics?
Yes.
So you are primarily client of this slide, this presentation, this part of presentation
Yes.
by one.
All right.
So this actually kind of shows you the charge transfer through time. Okay, yeah, so the background green color just means that it's the exact same right there as it was in the ground state. If the brighter the yellow gets, that means the more negative, you know, the more negative the charge density is right here than it was back in the ground state. Basically, it means that there's an electron hanging out right here. Or multiple electrons, depending on what you're doing, I guess. And then, vice versa with the blue, the darker the blue, the more localized positive charge is right there. So that means that there's a hole present there.
So if it's the same color going this way, does that mean the charge transfer is constant?
That means that the charges are actually kind of more or less stationary throughout that time. Because time is moving this way. So if there's nothing changing right here, so like, you know, throughout this part of the trajectory right here, you kind of just have holes hanging out like on these cesium layers, and then you have electrons hanging out, you know, in like the p orbitals just outside of it, is kind of what you can see from this right here. And then after you get to about this point, you can actually see the, you know, how it's getting blue up in here now, right in the titanium dioxide. This is actually a charge transfer right here. So you can move a hole over, but in this model, unfortunately, the electron follows suit pretty shortly after. So you get like an initial hole transfer over into the titanium dioxide, and then the electron follows suit shortly after, is what you can see, you know, kind of from this blue, then yellow, and blue, I guess. Yeah, so this shows that you actually get like an excited perovskite, and then it just turns into an excited titanium dioxide nanocluster. So, yeah, at the end of the day, it doesn't result in a charge transfer, but you do get a really brief backwards one from the application that was intended for. Yes?
I'm just wondering one thing, you know, like initially it's like spread over more space and it's very intense color that's indicating that higher intensity of positive or negative charge,
Yeah.
right? And after the transition it's become very light color, also it's localized on a small area.
So,
what's happening in the total populations of the positive and negative?
and again, like I don't, you know, it's kind of all blocked out right here, but like this color right here, this is actually like the most intense electron localization right there. Like this darker kind of like reddish orange, this means that there's like a little bit of negativity there. Yeah. So it's kind of, you know, a weak shell and then more or less a core, but then it gets really tightly bound right up there.
Right? I do not know the answer. I'm just
No,
theorizing
it's
on
not
the
a
fly.
question, it's actually
So
I'm just wondering
the
about-
both negative and positive charge can be in the same spatial
That also
vicinity,
can happen.
but in decomposition through atomic orbitals, they could take like p yellow on left and right in the p orbitals of lead, and this bluish can be also p orbitals of bromine, but they can be oriented like px, py, pz in different orientation. And if we integrate it
Okay,
on the
one
one-dimensional
dimensional.
slice, it will look like a sandwich, like orange, blue, orange.
Is it because
Make sense?
That's how I interpreted it. Especially because of the cluster, it's not like plane. So it's all the orbital or the densities kind of
That's
stacked on
one.
top of each other
Yeah.
in this picture. Whereas the other ones are you have more contrast just because it's layered.
Oh yeah, I think that was actually the projector messing with me because on this screen it's definitely a lot like brighter right here than it is up here.
But if you summed the time step, you would get 0.
Yeah,
Correct.
so you should.
Yes,
So it's
because this
just
is a neutral
showing-
system and we just plopped an electron in the hole.
It's
you know,
just showing how much it deviates from the ground state.
Correct. Yes.
So although
So this tells you where the extra charge is, more or less.
we're like migrated.
Yeah.
So like the early time is more perturbed than the later time. Because you have bigger differences.
What do you mean by more perturbed? I guess that's what I'm
The
confused
electron
about.
density is less like the ground state than it is at late time.
I guess it calculates
Yeah.
separately.
Right and wrong.
Kind of, yeah,
Yes and
I mean-
yes and no. Here the electron and hole densities are subtracted from each other, and even if there is an excited state without charge transfer, it is substantial deviation from ground state. If deviations happen in the same spatial region, this diagram may not reflect it adequately.
So is exciton is transferring to the dye, not just a whole.
Yes. And should I link as Dexter?
Yes, the Dexter energy
energy
transfer. So that's what those look like on the green figures. Whereas, so this was the isopropyl model, the hydroxyl model where you actually end up with a charge transfer. What you ended up with, you know, in this region was kind of blue down through here, and then yellow kind of scattered up through here. So you actually have charge separated between your species at that point. Okay. So, when I was trying to run this code for a long time, it would basically just take forever. I mean, it would take me hours to even get, you know, a couple of those pictures. So like if you notice it running really, really slowly, but it's not crashing, and, you know, say you just kind of stretch out your picture a little bit, like this green figure, if you just kind of bring out the corner a little bit and it has to reload and that takes, you know, way too long, what might be happening is that your figure or your graphics renderer is what's slowing you down. So in Linux, at least, you can change it like this. I was never able to find like an option in MATLAB, like a menu option. There is a way that you can change it once MATLAB has started, I believe. But if you, this would work on Mac, I would think. Windows with that command terminal, I'm not really sure if that would work. But within the MATLAB folder, this is the actual program right here. So if you open it with this tag on it, instead of using the default painter's renderer, it'll open it up with the OpenGL renderer, and this made things actually bearable for me. So if it's running super slow, try that. Okay, so once you have your green figures, yeah, just like for reference, I mean, I don't have it on here, I guess, but if you wanted to throw a color bar that kind of shows, you know, what's more or less intense, I guess, on either side of the spectrum, you can just do that with, you know, insert color bar and it'll just plop it right in there. And this right here is the code that is responsible for making this figure. And I can't remember, I feel like there was some kind of issue with, you know, putting in the angstrom symbol without having done this line of code down here. But if you know LaTeX commands, you can just straight up put it in and you just tell it that you want to interpret it through LaTeX commands. So this, you know, /AA turns into the angstrom symbol. So you can do things like that. But yeah, if you're going to be making a bunch of these and you know that you want something to be consistent throughout all of them, try to put it in this code here, because otherwise, if your computer is as slow as mine, it will take you forever to do anything. Okay, so There's really nothing. Okay, so whenever you do one of these figures, you're going to have different, like maximum and minimum values, which determine the color here. And so what will end up happening is that you'll get, like a bunch of these different figures, and they'll have like slightly different background colors and whatnot, and they just kind of don't really match, and it makes it sort of harder to look at and interpret because there's already a lot going on there. You can keep them all consistent by going into this color map menu right here, and just setting the min and the max to the same values for all of your green figures. So basically what you have to do is just figure out, what's the maximum and the minimum, or, give yourself a little bit of cushion. And then as long as all the data lies within that, you'll have the same kind of center point for each one, that background green color, and then everything will sort of be on the same color scale. That's, I think, all I got.
Okay, well, thank Landon. Any questions specifically, especially from Kevin and David? So if you have questions, but I'm not sure to ask in public development, type to Landon as an email.
Yeah, I spent a lot of time making those. If you're having issues, let me know.
Okay. Let's thank Landon once again. The next talk is by Dr. Fatima about how all these procedures change if the momentum is treated explicitly.
So I'm going to talk about the electron dynamics calculation, or really solid dynamics, momentum. So in this calculation, momentum is not conserved here. So in order to calculate electron dynamics, for that we need to get rate field tensors. So I'm going to start from rate field tensors. So if you want to calculate rate field tensors, you need three kinds of files. Number one, all coupling files. Here are direct and indirect transitions. Direct transition means when the momentum is conserved, and indirect transitions when momentum is not conserved. And number two, all energy profile fields. I wrote all because here for my calculation I considered 4K points, so 4 energy files. Each file contains the number of orbitals you are considering for your calculation. And number 3 is MATLAB-III. So now I'm going to explain about the coupling file. So you need to have, in this calculation, you need to have two kinds of coupling files, direct couplings. This kind of coupling files should have couplings of orbitals at same K point. And the format of the coupling file for same K point is coupling dot. This is the K point, and this is the answer. And for each K point, there are 892 points. And another kind of coupling files, that's indirect couplings. Here, coupling between orbitals at two different K points. Orbitals. So this would be K point. Okay, and the format of this coupling is coupling dot K point 1. It might be K point 2, K point 3, like two different K points, or same. And this is the number of time steps. And there are, for suppose if this is K point 1, K point 2, or K point 1 to K point 2, there should be 892 points. I had this number of files. For different calculation, it might be different. Okay. And number 2, this is so for each energy profile for each point, you should have certain number of orbitals and the arithmetic orbitals.
So, are you aware of anyone trying to use these things in 2 and 3 dimensions, or by now you are doing only for momentum changing along 1 dimension?
Mm-hmm.
So, which type of nanostructures it would apply to? Would it be applicable to was it ever applied to thin films or bulk?
I did not.
So which structures?
It is nanowire for
Okay.
me, for my calculation.
Okay, because for
Yeah.
any more any additional dimensions will be too many of those energy profiles
Yeah.
and other. So it's only the beginning of implementing momentum resolved dynamics, and by now it is made only for 1-dimensional structures to make this effort a little easier. So Kevin could be potentially interested in maybe in the future.
Okay. Okay, number 3, method probes. So here you can see 2 names. I believe John was knows well. So this for this for calculating rate field tensor, first part of this MATLAB code would calculate rate field tensors for same K, like 1 K point only, suppose at gamma point or 0.25. And once rate field tensors calculation is done for all the K points, then this part of this code will calculate rate field tensors between 2 K points. Suppose from that, I can show you here. So this kind of rate field tensors. This part of it. Once you once this part is done, there should be 16 different rate field tensors files here, as you can see. Now the last part of this code, this one, this code will make a super tensor which will contain that 16 rate field tensors files that I had shown before. So in order to do that, we consider 2 super indices, big I and big J, and this big I contains K, and so K means number of K points, 1 to 4, and this number of states is the total number of states we are considering. And this J is contains another 2 indices. This K, big K is number of K points, and this J is the total number of states. So all then we should have this super tensor, which contains all the rate field tensors for direct and indirect transitions. And this is we don't need this one for further calculation.
That's one. Do you make an experiment? What would happen in results if you remove this absolute value in this? Yeah.
No, I didn't.
Because there are some open questions in this direction of research, and it is related to what Yulun has presented and we discussed here, the detailed balance, which needs careful account of energy difference between source and target states. And typically in all of our calculations, energy list provides in ascending or descending order. But as soon as we mix in several lists, depending on k factors, it may flip the order, and then a detailed balance can get corrupted. It may be a source of additional errors, and one needs to take special care. So in this aspect, not as a source of result, but as a little debugging tool, removing this ABS and checking what happens could be helpful.
So this one, finally, once the report is done, then we should have these 2 points. This one, super tensor. And what is energy? Big energy pop? I am going to explain. Okay. Here, this matrix shows how the red field tensors are arranged in this super tensor. So first, red field tensor between k.1 to k.1, and then k.1 to and so on. Once the red field, we have this super tensor, we can calculate dynamics calculation. In order to do that, we need 4 kinds of files here. You can see this is red field tensor, and this is the file where total number of orbitals should be. So for each k point, I considered 80 k points. 80 orbitals. And I considered 4 k points, so there are 320 orbitals of this file. And the arrangement of these files is like this. Number 3 band out and file, and number 4 to another network out. So as you can see here, you need to fit the initial steps here, and then you need to use this code. It will load this energy pop and this red field tensor momentum. There is another code for this momentum calculation. And here this homo is the homo and lomo for their homo lomo for this file, not for individual components. So here homo is 160 and minimum is 1 and maximum is 320. And once you run this code, you should have this dynamics figure and waves. This is just showing how the electron and holes are relaxing to the band axis. This code is not
So x-axis is momentum.
and y-axis is energy. And that's all.
Okay, well, thank you, Fatima. Yeah, you can just loop this movie so that it repeats again and again. And other questions to Fatima? If no, I thank her once again. Aaron, you start, you stop with if time runs out, you continue next time. So what we were doing before was computing dynamics for singlets without taking care of spin. Then we, in Fatima talk, we did include into consideration exclusive momentum, and there is a way to do the same dynamics for spin polarization, where alpha and beta spins are processed independently in the same way as for singlet. And we skipped it this year, but there is a way to combine treating alpha and beta spinners, and Aaron will likely teach us how to use it.
Yeah, I don't have a lot to say because it's basically the same as all the other scripts we run. There's just one snag I came across that can screws up the code a little bit, but it doesn't change it. It's a simple fix. So these are the location of the scripts I'm going to be talking about today. So I guess I went a little ahead. So the only ones I'm going to talk about are the ones that have SOC in them. But yeah, they're on the photon, and they're in the bin, and they're spinner dynamics, the MATLAB codes. And so I guess today I'll just be talking about how to generate green figures, but it's basically the same protocol, just making this blue figures. So you have to do all the same steps that we did before. You have to get your RRR file from the couplings that you compute using spin orbit couplings, or the spin orbit interaction. And then you need a certain version of the code, so the MATLAB code, and then the other usual input files like energy path and input overlap. And so you just have to input the same usual parameters, so your initial conditions, some things about your cell size for your atomistic model, what orbitals you care about. So you have to do all those things. And then usual run the code, and then it'll spit figures at you. And it took me a while because normally like the axis is longer and this propagates. You usually assume it fully propagates. But after a while, I noticed that if I extended the time of my dynamics, this and time wouldn't change at all. And apparently, for the systems I deal with, the HOMO and minimal bands are both degenerate, and then it runs into some sort of numerical instability, because it will basically reach a steady state at some point, and then the wave function will be corrupted, and it will just give you a bunch of NAs instead of numbers.
And what's the reason for that?
I don't know.
But you guess.
Some sort of instability of, I don't know why, because the rates, because it has the rates and it's just going detailed balance.
But
from one state to another.
Maybe, if not the complete answer, but at least the practical feeling in which situation this numerical instability happens, and without much of deep analysis, any practical hints to avoid it. Right now you will show how to hide it under the rug, because basically nothing practical happens. It's already on the HOMO level. Mm-hmm. But how to avoid formation of this not a number values.
If you just have like, I don't know, maybe a 0.05 EV difference between like your HOMO and HOMO -1. Because for mine, it's like maybe less than a milli EV. Or it's probably not less than a milli EV, but it's like a milli EVs.
Degeneracy.
Yeah.
Is by the guy.
Right.
You're dividing by 0, right?
But one of us was running into and successfully resolving this issue. Will you share your...
Did you try to modify the triple R file? Like, how many coupling files do you use for generating the triple R file?
How many couplings do I use? Like a couple hundred.
Consider to decrease a little bit, like use 100?
I've tried doing like 20, 50, generating RR files with different amount of couplings or different amount of noise in them essentially. And yeah, they didn't really have an impact.
But in your situation, what's your observation?
At least for the green figure. So if you use long trajectory, you are very likely to get the noise, numerical instability. If you reduce the duration of the trajectory, then you can remove the numerical instability.
So we started today with talk by David, who did show how to convert long trajectory into set of constant coefficients, right? So it was a way to remove noise. And the longer trajectory, the better is the way the noise is removed. But in case, what Aaron is showing, sometimes absence of noise has adverse numerical effect. So a little bit of noise helps diagonalizing matrices, some random values here and there numerically. And it's a practical hint, making an average or shorter trajectory in some cases can remove this not a number numeric. And this is interesting phenomena that we all can investigate. So it's not computational chemistry or physics, it's more applied math problem, but it's an interesting phenomenon. How convergence of matrices and importance of having random values across the matrix.
And yeah, I tried a bunch of different things, changing time steps, changing time of integration, or the time of propagation. Nothing really changed, so I guess since we know we already relaxed at the band edge, and we're already like 10 picoseconds, going on 100 picoseconds past going to equilibrium, like just a cheap solution is just called frozen propagation. So basically you just find where your wave function's calculated, and then you just tell it to keep looping through and keep that value before it gets to the point where it reaches the instability. So like in the previous picture, like you would just rerun the simulation, but you would tell it once it hits this value, just propagate it forward from there.
So just project last legitimate value to all other subsequent timestamps.
And it's mostly just to make the figure look better, because I deal with radiative systems and their lifetimes are on the scale of a nanosecond. So you usually want your figures to correspond with the time scales that you're doing. And so, yeah, that's why I had to figure that out so I could get this propagate to about a nanosecond.
Is there any difference in relaxation time when you're using the frozen propagation?
Well, I guess if you change the time steps, if you should reach like a convergence point in general. I guess switching from like the scales I was going from, so I was like, for these I usually do 2,000 time steps. And so switching from like 1,000 to 2,000 didn't really change it. But I guess if I went to like 500, I would probably start to change the cooling times. And that's for generating green figures. And I guess I started doing ways to generate visualization figures.
Oh, and you want to give credit to Landon.
Yeah, I might let him do that because he knows the scripts better than I do, how to explain them. Because I don't quite understand.
Been a while.
But, yeah, please keep going, but we can return back to observables with more focus next week.
Okay. Well, I guess. So we need a lot. So for these, so basically this image right here is part of a movie. It's a big snapshot of a movie. But so all these dots and figures are from the atomistic model. So you have to generate the position file. So we have to get that and then extract this out. Then these ISO surfaces are the orbitals. And so to generate these, we need par charges in your orbital window from your input overlap. And then we process those so we can make figures like these. And so to get the orbitals, you need your par charge files. There's a script that Landon developed. Or I guess he started the development of it, and then Dmitry took it and applied it to par charges. And you just have to format the files a little bit so that MATLAB reads them correctly. And so that's just for generating what we call band out 2D. So that's just projecting the orbitals onto 2 dimensions. And then to generate the figures, you need the band out 2D that we made, and then RRR, energy pop, input overlap, like the usual dynamics. And then there's a special version of the code listed here, which is in the bin. And it's basically all the same code that we've gone over before with an extra 100 or 200 lines. And then to get your stick figures, you have to modify the postcard a little bit. And so to generate your band out 2D, you first have to make par charge files. I didn't go over that. I don't know if someone already did. You probably learned at some point how to generate par charges for your model. And so if you need questions with that, or if you need help with that, you can ask questions from someone. So you generate all your par charges, and then you have to trim them. We're basically removing like 100 or 200 or whatever lines, so that it's easier for MATLAB to read the code in. And so this is a script that's also in that bin, which basically just it loops through all the orbitals. So that's what these numbers count for. So it loops through your orbitals, and it just removes this many lines from the top of the par charge file. And here's some examples of what the file should look like before and after. So this is what the par charge looks like to begin with. So basically it's like your postcard file at the top of it. And then you delete, in my case, about 1,000 lines. And then you get it to this point. So where it lists the grid points for the par charge and then all the orbital data. So in general, I guess it would be however many atoms, how many atoms you have in your system plus 9. That's what the white box number should be here. So you make all your par charge files, and then you go to MATLAB and you open up the trim parch2x.m. And so to begin with, this is the part that Landon wrote. It basically just reads in the dimensions of the file. And so lockpot is just a dummy name, so you just copy one of your par charges to lockpot.trim so that it reads into the dimensions.
So this specific part of code is major insight that no one was able to do before Landon.
Mm-hmm.
It's a big challenge to read this specific output of computational chemistry codes. So it's very appreciated that you do it.
And then, like usual, you have some parameters for the orbitals that you have to input. And then after that, it's basically just hit run and hope it keeps saying I'm alive. And then yeah, after that, it'll just generate your band out 2D. And it'll save that into your directory, or yeah, whatever folder you're in. And so that gives you your orbitals for your dynamics, and then if you want to be visually pleasing, you want your atoms to be with your orbitals. And so to load that into MATLAB is, I don't know, it's kind of tricky, but Dimitri, I guess, during ESP last year, just took an afternoon and figured out how to do it.
It's not a silly activity because everyone who writes new drawing and visualization computational chemistry codes does it, so it was not elegant repetition of standard things.
So essentially the way that it works in MATLAB, what you do is you get your postcard.xyz, and then you basically copy that into all the chemical elements you have in your model. And so I only have listed one here, so you copy your postcard to, like if you have carbon, so you go with CXYZ. Then you would do the same thing if you had hydrogen, you'd do another version of hydrogen.xyz, and so on. So for all the chemical elements you want to visualize, and then you remove the first column from each of your files. And then the first column is usually just the, actually I gotta back up one step. So after you copy your postcard into C.XYZ, you want to delete all the other elements. So if you have carbon, so if you want to isolate carbon, you basically just open up your C.XYZ and just delete everything else that's not carbon, or all the lines. So you just have carbons in there. And then you would remove the first column from that file. And then in this case, we usually name the updated files carbon1.xyz. Or you can name it whatever, but I think in the MATLAB code it reads that in. And so the visualization code is basically the same as everything else before, so you have to put in your usual parameters. And then you get to around line 300. And then you start getting into where it reads band out data, so you have to manually enter the dimensions. So those are the 3 numbers that were on top of the par charge files, which was the grid points. And below that, that's the code that visualizes the atomic coordinates. And so this would be the carbon atoms would just load in your C1, and then for all the other chemical elements, you just load in XYZs. And from there, basically just, if you want to draw bonds between your chemical elements, you can make vectors between them. So, I don't know, there's probably like 20 lines of code in each one of these, but basically just gives distances between each of the atoms, and then within a certain tolerance, it just makes a vector of a certain color. And for mine, it's pretty straightforward, because I'm just dealing with my perovskite nanocube or your quantum dot all the time, so I don't have to change this. But if you were doing your own model, you'd have to change these a little bit. And you basically just have to change the names of the chemical elements to whatever your model is. So they correspond. So that gives you bond distances, and then a little bit below that, that's where it starts saving the video for the file. That's where the code kind of starts to lose me. But there's 2 inputs you have to put in. So your number of conduction bands and number of valence band states. If you don't change those, oh yeah, they correspond to your band out. So yeah, if you put in the wrong numbers there, you'd have like the wrong HOMO for your dynamics figure. And then, yeah, from there is click run, and apparently it's a heavy-duty calculation to do, because I think on my Mac laptop, like, it just starts heating up right away afterwards, and it has to sit there for 10 hours to do the whole trajectory. So it's best practice would be to find a desktop that you don't really care about and let it run on that overnight. And I think that's it.
Okay, let's thank Aaron. You didn't include the movie that comes out of this calculation.
I didn't. I couldn't find one on my desktop. And I couldn't find your YouTube page for some reason. Well, I found one of your YouTube pages. I couldn't find the other YouTube page.
Well, maybe we will just enjoy the movie next time.
Yeah,
we'll
it'll
find
come
it
up.
together. Any questions to Aaron? The last part of his talk was not mandatory. It's a little exhausting and special effort for visualization. But the first part was something. Questions 1, questions 2, questions 3. Let's thank Aaron once again. So either sign up black star piece of paper. Okay. Okay. I'll process and inform everyone of the choices. So it looks very, very reasonable. I'll probably just arrange it in so there will be repetitions, and if anyone took too much, we'll find a way to dilute. So what? No one took this part, and I'll ask someone to focus on it. And if time allows, I would be willing to cover it myself, but it may be not possible because of time. So it's the part of rates for relaxation was already covered today.
I volunteer.
Okay. Thank you for being brave. Yeah, it will be very applicable to your project if you do it. Okay. Yeah, that's great. And I think Yulun has volunteered for 60% of all questions. Right. Well, we'll find a way to make it. Yeah, many thanks for volunteering. Yes?
So will you send me reference materials to help
Oh,
me
yes,
prepare
yes.
for the topic suite?
I do have a version of the code that does it.
Okay.
And it is very, very simple very, very similar to what Yulun has presented at the end of his presentation, and what Levi was putting under debate for exponential fitting.
All right.
It's just fitting of different function, but it is a similar procedure. And I do not see David.
That's because they passed it around while I was talking,
Oh, okay.
and it never made it to me.
Well, you have chance volunteer to several topics and override choices of others. And you better select yourself and do not let me to select instead of you. Well, let's finish the meeting. Thank you for investing time, and as soon as we complete with these practical skills, we'll get back to regular life of research updates, maybe a little bit of literature club, and polishing papers, and maybe making new discoveries together. Okay, meeting is dismissed. Have a nice evening.
You want to take the long route with me outside? You want to take the long route with me? Since you enjoy a little walking?
Yeah.
The call will be disconnected.
Are you still able to come to